Hello, everyone. I'm Bobbin from Polygon, and I'm here today with Pratyush from Aleo, and we're going to be talking about how to achieve decentralized private computations and how ZKPs tie into that.
Hi, everyone. Fantastic to be here. So I'm Pratyush, and I'll be talking about first, I guess, what privacy actually means in the context of blockchains and when computation is involved, and then we'll see how existing systems fall short, and then how we can use zero-knowledge proofs, as Bobbin said, to actually improve the state of the art with respect to strong privacy. Okay. So I guess the starting point should be how existing blockchain systems work and where they fall short in terms of the privacy guarantees they provide. So if I take existing system like Ethereum or something, right? So let me just make sure this works. So what happens there is that there are some miners or validators which maintain this list of blocks, which is the blockchain, and let's just call these entities M1, M2, whatever, right? And they're responsible for appending a new block to the blockchain whenever, at some regular period of time, right? So what does this new block actually consist of? So let's say I'm a user and I want to publish a new transaction to the network. What I will do is I will send my transaction to the network, to the miners, right? And then they will check that this transaction is valid before they append it into the sort of to-be block, or the new block that is going to be added. Right? Now, what does this transaction validation actually look like? So in the context of these smart contract blockchains such as Ethereum, what these miners need to do is they need to re-execute the computation that is occurring or is claimed to be occurring inside the transaction. So whatever smart contract is specified by this transaction, they need to execute the code of that smart contract on whatever data is specified inside the transaction, and make sure that the transaction is authorized by the correct parties, whoever is supposed to authorize the transaction. Okay. So this re-execution happens with all the nodes in the network, and then if I want to check the history of the chain, I have to again do the re-execution of every transaction in every block from the beginning till the present, right?
That seems to be problematic in some ways.
Yeah, so re-execution, it's a very nice and simple strategy, which is why everybody uses it. Every blockchain that I know of uses it to check that the transaction is valid. But it actually causes two kinds of problems. First, from a scalability perspective, the issue is that this transaction, the code in there has to be re-executed by every node in your network, right? And then if your network contains nodes with different computing powers, so say a supercomputer, a desktop computer, and then maybe just a phone which has a very small computation ability, then if your transaction is heavy, then maybe only the supercomputer and the full desktop node can check the transaction in time, right? And this is a problem when we have many transactions in the network, which we do want because we want to scale up our chains, right? So there's like many transactions coming in every given second. And what will most likely happen is that our computationally weak node will not be able to keep up with the rate of transactions that are coming through, right? So we're limiting the kinds of nodes that can participate in checking the integrity of our blockchain. And this is not something we want, especially when we claim to be a decentralized network. Okay, so that's from a scalability perspective. From a privacy perspective, the issue is that each transaction, it reveals at least three kinds of data. First, to re-execute, you need to know which program you're executing, right? You need to figure out, okay, I'm executing, say, a payment smart contract or something, ERC20, so I need to execute the code for that. Then you need to know what data is being provided as input to this program, right? So this is information like sender, recipient, value in an ERC20, so on and so forth, right? And finally, you need to know the identity of the person who's authorizing or participating in the transaction, right? So you reveal information about the participants of the of this transaction in particular, right? And this information sort of is encoded in this transaction. And once this transaction goes to the blockchain and is enshrined there, it sort of lives on the blockchain forever for everyone to see. And indeed, it needs to live there because if I want to check the history of the chain, I need the transaction to execute to make sure that the state was updated correctly, right?
I think in regards to so these are clear. In regards to anonymity, I think even the original Bitcoin paper, at least the claim was that you can separate because we don't actually know the participants, we only know their keys. So maybe there is some degree of anonymity there.
Yeah, so that's a good question, right? So maybe it's clear why we want to hide the data that is being provided as input into the transaction. But if we, for example, this participant is actually not like, say, Pratyush Mishra here. It's public key 0x59, whatever, like some random looking string, right? So it doesn't actually reveal directly my identity. But the problem is this sort of guarantees what's called pseudonymity, right? So just a different name for my identity. And the problem is that, say, if I reuse the public key that I use in transaction 1 in another transaction, then anybody can see that these two transactions were executed or authorized by the same person, right? So then they can see exactly that I'm using this public key the same person is using the same public key to pay for coffee at Starbucks and then participate in some complex DeFi protocol. And then this can cause all kinds of problems, right? So if they know that this public key is owned by a whale and that whale goes and shops at a particular Starbucks, then maybe you could have you can stalk that whale. So basically, pseudonymity doesn't really lead to any sort of strong anonymity guarantees because you can piece together pieces of information and then build a profile of the person that is behind that public key.
Yeah, and I think even in everyday transactions, let's say you're receiving your salary payments in some account, you don't want to necessarily transfer money from that account to your friends because you don't necessarily want all your friends to know how much money you're making and all of that stuff.
Yeah, and if you're going to the doctor for a particular treatment, you don't want the world to know that you're going to a cancer specialist. So yeah, the sort of lack of privacy from that perspective, or this anonymity, really impacts every aspect of a person's life because finance interacts with every aspect of a person's life. Also, from a fungibility perspective, from the integrity of the currency perspective, you want each coin to be equal to every other coin, right? So if I give you $1, you shouldn't say, okay, this dollar is only worth actually 80 cents. You wanted every dollar to be worth the same. But with Bitcoin, for example, Ethereum, I can go and see, okay, this Bitcoin was used in this transaction, which was part of some criminal activity, right? So actually, I don't want to transact with that. Or if I transact with it, I'll only, value it at 0.8 Bitcoins or something like that, right? So now you've lost this fundamental property of the currency, which is that every unit is exchangeable for every other unit.
Now, we talked about Ethereum and Bitcoin, but the models there are slightly different, right? Ethereum is account-based and Bitcoin is UTXO-based. So
yeah.
Basically, there might be a claim that UTXO-based systems are better than account-based systems. So I'm curious how you think about it.
Yeah, so maybe let's take a quick look at the difference, right? So in the UTXO model, basically what happens is that there's a list of accounts, right? And then when you make a transaction, you update the state of this account, which is saying the sender's account, and update the state of this account. So I'll subtract the value of the transaction from this account and add the value of the transaction to this account, right? Now, privacy for this is quite difficult because you need to hide which entry in this list is being updated for every transaction. And while we have some crypto techniques for that, they're not very efficient and probably in the context of blockchains, the most efficient thing would be to somehow update every entry in the sort of list of accounts, some with dummy entries if they're not participating in the transaction, and others with actual entries if they are participating, or with actual updates if they are participating in the transaction. So in the account model, we have it's very difficult to achieve any sort of anonymity. So that's why existing work on achieving private payments and private computation actually focuses on what's called the UTXO model, which underlies Bitcoin, right? So maybe let's quickly just go over what the UTXO model looks like. So basically, in a UTXO model transaction, what you have is you have some input coins, right, and some output coins. I'll just say one input and two outputs for now, right? And the idea is that these sort of split, you're sort of in some sense consuming your input coin and creating two new output coins, right? And so basically you maintain in some sense a set of, active coins or whatever, right? Unspent coins maybe. So in Bitcoin parlance, this would be like UTXOs, right? So when I construct a transaction, I consume or I take some UTXO to the output of some previous transaction. So this came from some, TX prime or something, right? And then I produce, and then I mark that UTXO as spent now, right? So it becomes like, I guess, a STXO. And then I produce two new coins, right? C2 and C3, which are then appended into the list of active unspent coins, right? So these are now the new UTXOs in the in our set of active coins.
And what are key properties do we want to check when we execute this transaction? We probably want to make sure that we didn't create any new money or something like that.
Exactly, right. So this is what the transaction looks like, but what does a validator need to do to check a transaction is valid before appending it to the blockchain, right? So maybe I'll write it here just to keep it separate from things you might erase in the future. So the first thing you want to do is you want to check that the UTXO that you're spending, that the spent coin is, I guess, exists.
Is active still or something.
Yeah. Is active, right? Or was active before the transaction, right? Mm-hmm. And you need to check that, it is authorized, right? So basically, I'm not spending somebody else's UTXO, right? Only the person who owns this UTXO is able to consume that UTXO or spend that UTXO or that coin, right? So that's one. The second property is you want to check that value balances are preserved, right? So check that value is conserved. And what this just means is that the sum of the input and output values is equal, right? So the value of C2 plus the value of C3 should be equal in this case to the value of C1.
And because of this, you basically lose data privacy, and because of this, you lose the anonymity, right? And I guess if it's not just simple checking if it authorized, but like if there is a complex program that is there, that's where you will lose the functional privacy as well.
Yeah. So this is we're talking about these chains which support general computation. Bitcoin is a chain which just supports one computation, which is transferring money. And in that case, the computation is checking that the value is conserved, right? So coming to your point of data privacy versus anonymity and so on, right? So you're completely right that these two steps or these two properties are the ones which harm the anonymity of users. Because if I need to check that the C1 that I'm spending in this transaction was not spent in a prior transaction, I need to have some unique identifier for this C1, which I can then refer to in the list of active coins and check that, okay, C1, the identifier of C1 actually lives inside this list of active coins, right? And then I can subsequently cancel off that identifier once I've spent C1 and then append the identifiers for C2 and C3, right? But now, because this identifier is unique, it allows me to link C1 to the transaction that created it, right? So then I'm able to build this transaction graph going backwards of, sort of every ancestor of C1 in some sense. This, completely harms privacy. And then finally, also if I need to check that the spender is authorized to spend this UTXO, the simple way to do it is to, include a signature over the transaction. But the signature has to validate against some public key, and whichever public key that signature validates against, in this case, it would be the signature of C1 for the public key associated with C1, right? that public key again reveals the pseudonymous identity of the person who is sending the transaction, right?
So how do we bring ZKPs to help with this?
Yeah, okay, so that's a fantastic question. We'll start with what is the easier property, which is first, showing how we can enforce that value is conserved without, while hiding what value is actually participating in the transaction, right? What is the sender value, recipient value, and so on.
Yep.
Okay, so maybe let's see how we can do this one first. Okay, so what we will do is if we actually open up this thingy a little bit, so there's C1 and there's some, abstractly there's some value associated with the coin that you're spending, and there is some public key associated with the coin that you're spending, right? Which, specifies which address or is the owner of this coin. Okay, so what we can do first is we want to hide this information. We want to hide the value is conserved and what the public key, maybe we'll just focus on hiding the value first and we'll come to the public key later. So what we'll do is instead of including the value in the clear, we will actually hide the value. Let me put this away under some sort of cryptographic hiding mechanism. In this case, we'll use what's called a commitment. So I'll just put a box around values that are committed, right? So there is a commitment to the value here, a commitment, similar commitment to the value here, and a similar commitment to the value here. Okay.
And just to clarify, the commitment doesn't reveal anything about the value, but it doesn't allow anybody to change the underlying value, right?
Yeah, fantastic. So just quick overview of commitments. You basically cryptographic primitives which allow you to you can think of them as lockboxes, which allow you to commit to some message, in this case the value, while hiding all information about what the message is. But you can't sort of open the same commitment to two different values or two different messages.
And I guess if I'm the miner, like how do I now check that, because I don't know what the actual values are, how do I check that this is preserved?
Yeah, so the hiding property of the commitments ensures that, okay, now these coins, they don't reveal any information about what value is inside them, right? But they also make it impossible for the miner or validator to check that the value is conserved. So how do we do that? And this is where we'll introduce our first use of ZKPs, right? So we'll include inside the transaction also some proof pi, right? And what we'll enforce inside this zero knowledge proof is first we'll sort of open up, we'll take as input all these commitments. So we'll take, I'll just call this C1, maybe CM1, CM2, and CM3, right? So we'll take CM1, CM2, CM3 as input inside as public input to the zero knowledge proof. And then we will open these, right? So we'll open all of these and then check that V1 is equal to V2 plus V3, right? So we'll just sort of just move maybe I'll write it somewhere here, and because we'll have some other stuff which will come in the middle. So we check that V1 is equal to V2 plus V3. So instead of having the miner perform this check, we just have the transaction constructor provide a proof that enforces this check, right? So we've moved the computation away from the miner into the proof itself, right? And the zero knowledge property of the proof system ensures that even though we're opening these commitments inside the proof, they reveal no information about the contents of the commitments. So no information is revealed by this pi about V1, V2, V3, right? So this allows us to get our value conservation check, right? So we're good on that front, okay? So this gets us data hiding, but now we still want to achieve anonymity, right? So how do we actually go about doing that? And there's basically, these two steps that we need to do correctly. Let's maybe tackle the second one because it's a bit easier. So what we'll do is right now there is this public key that is living inside the UTXOs, right? So there's the value which is inside the commitment, but also this public key abstractly which is living here. So what we'll do is we will move the public key also inside the commitment for this coin, right? So now the public key also, or the address, also lives inside the commitment. So we'll open this up, and then instead of checking whatever signature we were checking in plain, we will now just check the signature inside the zero knowledge proof also. Okay, so this allows us to move this is authorized check again inside the zero knowledge proof, right?
So the proof itself almost becomes like a signature, or it validates the signature.
In some sense, in some case,
yeah.
exactly, yeah, in some sense. Actually, yeah, if you look at how the first work to actually achieve this private payments in the space did it, they didn't have a signature, they used some other mechanism, like proving knowledge of the public key in some sense inside your zero knowledge proof. So that's how they did it, right? So, okay, so now we're almost there. We've achieved data hiding and then partially anonymity. But we need to check that the coin that we're spending is active without revealing which coin that we're checking, which coin it is that we're spending, right? So we need to provide a way for the validator to check that the coin is the spent coin is actually, the correct coin, but while hiding completely what that coin is. So the approach taken by Zcash, which is, as I said, this first work for private payments in the blockchain space, what they did was they said, okay, instead of having this list of active coins, which is updated and as transactions come in and out, we will just have this ever-growing list of commitments, right? So we will have a list of commitments, right? And as new transactions come in, we will append the output commitments to this. So, right, so if we have some list, when this transaction comes in, we will append, like, say, C2 and C3 at the end of the list. Additionally, we will build a Merkel tree over this list of commitments. We can call this the commitment tree. And then the main, I guess, one of the key innovations of Zcash was instead of providing the commitment of the UTXO identifier in the clear inside the transaction, we just have the transaction constructor prove that the commitment actually exists, right? So this allows us to ensure that the commitment was created in some past transaction. It is the output of some valid transaction that happened in the past, right? So what we'll do is we'll check that CM1, we'll just check that CM1 belongs in the commitment Merkel tree. And we can do this via some standard Merkel tree authentication path checks, right?
Then Merkel tree also becomes the input.
Exactly. So you will need to provide additionally the root of the Merkel tree, and then the validator can check that this claimed root that we're providing as input is actually the root of some historical, like the root of the Merkel tree at some point in the past, right?
And I guess how do you make sure that the same transaction doesn't spend the same, like we used to mark which ones are active or not. Here there is no information which one has been spent or not.
Exactly, right? So now we've sort of, in some sense, gotten rid of this coin entirely from the transaction, right? Which is what we want for privacy. But and okay, so now we know we're spending some coin from this list of coins. But how do we know that it's not already been spent, right? How do we know that the CM1 was not used also in a different transaction? So to do that, you can think of this as the set of all coins. So what we need to do additionally is to make a set of spent coins, right? So to do this, we want some set of spent coins also. So just dividing this off, okay? And how, maybe I'll just draw the C1 in dotted lines to indicate that it is maybe in green to indicate that it is hidden, right? So this C1 actually does exist in the transaction. It's just completely hidden. So C1 is here, and there is a commitment which has the value and the public key, right? Okay, so now how do we maintain this list of spent coins without sort of linking the entries in this set with the entries in the set of all coins, right? So we want to be able to check that the C1 is not in the set of spent coins, but how do we do that without checking it against this list? Okay, so the mechanism that is used in Zerocash is basically you include inside your commitment an additional entry or additional piece of data called the serial number or nullifier. Now this is a unique identifier for the coin, right? Similar to the commitment, it's completely unique. There's one per coin, essentially. And the idea is that when I'm spending the coin, I reveal as part of the transaction the serial number also. So this is not hidden anymore. This is the actual serial number for the input coin, right?
Do you reveal the serial number or the hash of serial number, for example?
Yeah, so I'm hiding some details here. How you actually compute it is that you have some secret thingy in here, right? And then you hash that along with your private key that is associated with this public key, right? You hash both of those together, the secret key and the serial number nonce or whatever. And then you output the result of that hash. But for our purpose, I think it's fine to just assume.
I think the important property is that the serial number is in no way can be linked to the original coin that was.
To the commitment, yeah. So from this commitment, I have no idea what the serial number for this CM2 is. That is completely hidden. We have no way of figuring out. Like if later on I spend C2, there's no way to link SN2 with this CM2 at any point in time. Okay. So basically, I have this list of serial numbers. So let's say SN1 blah, 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 up to like SN or whatever, right? And what the validator does is when they see the transaction, they check that this serial number that is input in this, that is provided as part of the transaction is not in the list of spent coins. And the zero knowledge proof asserts that you also provide, instead of providing CM1, you provide SN1 as input, right? And then you check that SN1 is the serial number for CM1.
So in this, to check the validity of that the coin actually exists, we use a Merkel tree. Why can't we use a Merkel tree for serial numbers? Why don't we, instead of outputting a serial number, just include the check for a serial number in the proof?
Yeah, so that's a good question, right? So a priori, we just have this set of spent coins, which keeps growing as you spend more and more coins over the lifetime of your system, right? So if I have 2 to the 30 payments, then I will have at least 2 to the 30 entries in this list, right? And this is going to hurt the scalability of our system. One way to work around that is instead of having the validator or miner check that the serial number is not in this list, we can have the proof itself assert that, right? So we'll build, as you said, another Merkel tree. This is the serial number or nullifier Merkel tree. And then we can add another line here which asserts that, check that SN1 does not belong in this Merkel tree, for example, right?
But what would be a challenge with that? I mean, as far as I know, like Zcash doesn't do that, for example, right?
Yeah, so the main reason to avoid that is from the perspective of the user, right? They always need to use the latest Merkel tree root at every time step, right? Because otherwise what ends up happening is, so let's say I use the serial number Merkel tree from 10 blocks ago, right? I could have spent the serial number in those intervening 10 blocks and then nobody would be, the proof would still be valid because according to the route which I gave it, which is the 10 blocks old route, the non-membership proof would go through, right? But in the meanwhile, in the last 10 blocks, I've spent that coin, and so now I've double spent the coin. So basically, from that, that's the reason why we need to. So you could ask the user to always maintain the latest non-membership proof for their coins, right? But this means that if I go offline and come online, then I need to sync with the network, right? And
proof could become stale if like it didn't get through the network fast enough.
Yeah. So if it didn't get it in block 1, then I have to make if my transaction didn't make it into this block, then I would have to wait another block, as you said exactly, right? And then I would have to make another proof for that new block, and so on and so forth. So just is a lot of pain from a user ergonomics perspective.
So it's much easier for the miner to check this. But that probably creates another problem because this list of nullifiers is ever growing, right? You can't ever get rid of them.
Yeah, so what you can do, for example, is say, I'm going to have an epoch of maybe 3 years or something like that, right? And then all the coins within that 3 years, so I'll maintain like a serial number list for those 3 years, right? And then if I want to, so that, let's say that 3-year period gets over, then in the next 3-year period, I can enforce the policy that, okay, if you're trying to spend a coin which is from 3 years ago, right, from the last epoch, then you have to provide the non-membership proof, right? But for coins in this epoch that were created in this epoch, then you will just check the serial number. So basically, this maybe gets around the problem that your proof becomes stale because it's not like I'm asking you to prove non-membership. Like the 3-year-old epoch is always going to be a 3-year-old epoch always. So it's not like the Merkel tree for that epoch is going to change. So we don't have that problem. So you could, so that this way you could, this does harm your anonymity because it reveals, is it from, is the coin that is being spent from this epoch or from, some past epoch, and that sort of partitions your anonymity set a little bit. But, if your system has, the sort of scale where the list of nullifiers growing is a scalability problem, then your anonymity set is in practice going to be large enough. Like in 3 years, you're going to see enough transactions that your anonymity set is big enough.
Yeah, I think for like if you're dealing with like 10 transactions per second, you're probably never realistically going to face this issue. But if you're dealing with thousands transactions per second, then maybe.
Exactly.
And in that case, as you said, the anonymity set is big enough over a course of a year, or maybe even less than that. Who knows?
Exactly.
Yeah.
Okay, so this sort of basically is the high-level overview of how...
So this checks this off, right?
Exactly.
Nice.
So now we have... This is basically the construction of Zcash, which is shows how to achieve these private payments, right? So this is how you would get a private payment system on top of a decentralized ledger, okay?
So one issue with that is that this is like a fixed DKP. You're proving a specific circuit, so like you don't get the smart contracts or whatever else capabilities. So it is nice, you have private payments, but it's,
limited in functionality.
Yeah.
Exactly, yeah. So this is already, this is a big step for, we didn't know how to do private payments, and now we know how to do private payments, completely private payments. But, people have moved on from just doing simple payments with Bitcoin, and now the excitement is all in doing, all kinds of heavy computations or interesting computations with smart contracts, right? And this is also one computation. The computation is checking the value is conserved, right? But we might want to do something more complex than that, right? Maybe you want to do a decentralized exchange, or maybe you want to do some sort of auction. There's an unlimited number of things that you could want to do with smart contracts. And this doesn't support that. Okay, right. So where we stopped off, we were talking about how we achieve private payments. We want to achieve smart computation, smart contracts inside the same privacy paradigm, right? So if you actually take a look at this construction, the only thing which is really specific to the use case of or application of payments is just this line here, right, which corresponds to this check, right? So this is we're checking one specific program's correct execution, namely the the payment program or the payment application, and the check for that is just checking the value conservation. So to generalize this, maybe we just get rid of this specific step here, right? And maybe I'll just rewrite this to put the signature up above. So for check sig against PK. Okay, so these are all the checks which are sort of agnostic or completely independent of the application, right? And then we have one more, which is the application-specific execution, right? So we have some computation that is executing, and we want to check that it is executed correctly. And so then this check now becomes check that application executed correctly. Okay. Now the question is, where does this application live? What application are we executing? We'll get into that in just a second. Check, I guess, application execution. All right, this is the check that we want to do. Right, so, okay, which application, what execution, what data? All right, so let's just take a look at that. So right now we have a handle on, I guess, 3 things, right? So we have this input coin or something like that. Let's, instead of, since we're not talking about payments anymore, let's change the terminology from coin or UTXO to record, which is what we use in the ZEXE paper. And it's just some sort of, entity which holds some data, right? So a record has some data inside it. So we have an input record and 2 output records in this example. So the question is, what application are we checking the correctness of? And the answer is, in some sense, whatever application is specified by this input record, right? So what we'll do is inside the commitment, we will include, this is getting a bit crowded. Where did I put my, oh, the eraser is right here. So we just rewrite this a little bit. Okay. So we have our value, our PK, and the serial number. But now we will also have some program ID or something like that, right? So let me call this PID or something like that. Okay.
And is that a commitment to a program, or is it something else?
So for the moment, I'll leave it abstract, and we'll fill in the gaps of, how to go from PID to actually the application.
Okay.
Right. And so here, what we'll do now is, check that program for PID executed correctly. Okay, right? Now, okay, so this is fairly simple extension of where we were before, right? But this one change actually opens up a whole box, or Pandora's box of things in terms of that need to be done, because, okay, this is a very innocuous looking line, but you actually, to implement this sufficiently in a construction, in like something that you can run in some decentralized network, it's actually quite tricky. So let's see what the problems that we encounter are. So the first issue is that for all of the efficient ZK proof systems that we know, right, they all work, at least in terms of the ones which have the best proof size, for example. They all work with what's called circuits, right? And so the circuit is like some description of a computation. And they work with so-called fixed circuits, right? So you specify a computation as a circuit, and then you make a proof for that circuit, right? But this requires knowing ahead of time what that circuit is, right? And here, essentially, what we're asking for the zero-knowledge proof to do is say, hey, please maintain an open slot inside yourself for something that I can just plug in, right? So this program, which is going to be specified arbitrarily, I need to be able to plug in any arbitrary program, and then you have to make a proof about that. Now, the techniques we know to do this, there's quite a few, right? So one technique is what's called a universal circuit. So it basically has exactly this like slot where you can plug in the code of any program, and then it'll run and execute correctly. And you will enforce that the program executed correctly, right? Now, the downside for these universal circuits is that they're quite expensive in practice. They impose at least like a 10, 15, 20x overhead compared to if you just had like one hard-coded program in here, okay? So that's one approach. The other approach is, instead of checking that the program executed correctly, right, we can use what's called proof recursion and instead just check that a proof for that program executed is valid, right? So the proof that the program executed correctly, we instead check that in here, right? So let me just rewrite that. So let me erase this. and we'll just put program proof is valid. Check program proof for PID, right? And that's all so we've done this, right? Why does this help, right? If you think of it, taking a step back, there's no reason that this new check is more efficient than the previous check that we had of a universal circuit. And the key idea is, here's where we sort of leverage the succinctness property of these snarks, right? The idea is that checking this proof is going to be much cheaper than executing the program itself, right? So this proof, you can check it in, let's say, 10,000 or 20,000 R1CS gates, whereas the program, it might correspond to 1 million R1CS gates, right? So checking this proof is only going to cost 20,000 gates, no matter which program is being executed inside which corresponds to PID, right? So by doing this, we have one step of recursion to we validate just one proof instead of rerunning the program.
So basically, by using recursion, this is a fixed circuit itself.
Exactly.
And you can provide, the fixed circuit itself knows how to verify whatever proof, but then you can provide proof for any program to it, and it will still be able to verify.
That's fantastic way to put it. So now instead of having this circuit which has this empty slot to plug things in, right, now we've fixed the circuit. The circuit is always doing just these steps. It has some ZKP verifier hard-coded in, right? And then we can provide whatever input proof we want to that verifier subcircuit. And in practice, what we need to do for this is then this PID, it actually becomes a hash of, if you're familiar with SNARK terminology, there's this verification key which corresponds to the program for many SNARKs of interest. So if you take Grot16, Plonk, Malin, Sonic, etc., right? They all produce a short digest or hash of the program, which is called the verification key, which the verifier can use to check the proof, right? So with this PID actually becomes the verification key for the, so we'll call this VK for the program. So VKP, right? And this is again VKP. Okay, and I guess what I didn't mention before is that instead of having the value in here, we can have any arbitrary data. So I'll just call it D. But yeah, you can put whatever byte string you want in there. And then you will check this proof against VKP. So you can check the program proof against the VKP. And the idea is that this VKP is going to be, again, very small and of fixed size no matter what the program is.
Makes sense. And then so in here we had two outputs being generated. Does the circuit somehow is it flexible enough to say some programs can generate more than one output, 2 outputs, 10 outputs, whatever?
Okay, yeah. So this is a very good question, and it ties in to the questions of data privacy and function privacy also, right? So maybe taking a step back from this construction and going back to our properties of data privacy, function privacy, and anonymity, right? We achieve anonymity just because we didn't change any of the anonymity infrastructure from the zero cache construction. Data privacy, again, is preserved because they will only have opaque commitments in the transaction. And function privacy is achieved because if this is zero knowledge, right, we reveal no information about which verification key is being plugged into the proof, right?
Yep.
So the ZKP hides information about the program. So this gets us all three of our properties of sub-properties for privacy. Okay. Now the question is, what happens if this is one transaction? What if there's another transaction which has inside it? So let's say this TX1, for example. It had inside it 2 inputs and 2 outputs, right? This would require a different circuit for this ZKP, right? Which supports 2 serial numbers, 2 commitments for the outputs, and then potentially the proof would also look different, right? So a priori, there is no reason why we can't just say, okay, I'm just going to have different circuits for transactions with 1 input and 2 outputs, and another circuit for a transaction with 2 inputs and 2 outputs, and another one for 5 in, 3 out, whatever combination you like. You just fix it ahead of time and say these are the transactions that I would like to support, and you would have the zero-knowledge proofs for that, right? And then you have to make sure that your program that you're using actually supports that arity of the inputs and outputs, right? Now, so this is a thing that you can do very naturally, but it does hurt a little bit our guarantees of function privacy. And the reason for this is because if I know, for example, that program A only works with 3 inputs and 2 outputs, right? Then every transaction which contains 3 inputs and 2 outputs is a candidate to be program A. And if I know that program B only accepts 1 input and 1 output, then I know that there's not going to be any overlap between the transactions for program A and program B. So then I can use that to maybe figure out, okay, this transaction is definitely not program B. So that's sort of harming and partitioning our anonymity set for our various programs, right? So that's why in the ZEXE paper, what we did was we just fixed 2 in and 2 out. So you have 2 inputs and 2 outputs, no matter what. Actually, in the implementation, and the idea is that using this 2 in and 2 out, you can actually construct, any higher arity that you want, as long as you also support like dummy inputs and dummy outputs.
Makes sense. And then, so this is kind of an abstract construction. Like if we start talking about the concrete proving systems, I think in ZEXE in original paper you guys used Groth 16, right? So like, what are the different trade-offs of different proving systems here?
There's we have every year sort of new proof systems coming out, and it's a very fast-moving space. So there's obviously different trade-offs. So in the ZEXE paper, we use actually this proof system called Groth-Mahler 17, which in retrospect, we didn't need to use that, but basically it provides this property called simulation extractability, which is necessary for this construction overall. But anyway, the problem with the proof system that we had in that at the time of writing the paper is that if you've heard of Zcash knocks, you know often that they require this trusted setup to produce the verification and proving keys, right? Now for Groth-Mahler and Groth 16, these proof systems, they require the trusted setup to be performed once per circuit, right? So if I have, for example, the 1 in 2 out circuit, that will require a different setup from the 2 in 2 out circuit, right? And maybe this is okay, if you're just talking about a small number of circuits which do the same functionality, but in the context of arbitrary computation that is specified by the user, right? Now the user will have to, or the program developer will have to produce a trusted setup for every program that they produce, right? And the user will have to run this or trust this trusted setup was performed correctly for any arbitrary program, right? And so we know of decent techniques to reduce the overhead of doing this, such as the ceremonies that have happened for Zcash, and basically everybody has participated probably at one of these MPC ceremonies now. But yeah, it's a big hassle to ask that every time you want to deploy a new smart contract, you have to run a fresh ceremony with hundreds of participants, right? So ideally, you don't want to use Groth-Mahler 16 or 17. So what do you want instead? What we've done right now in Aleo, which is a version of a deployment of ZEXE, right, is we switched out Groth 16 for Marlin, which is a proof system which has universal setup. It's like Plonk or Sonic. And the idea there is that this verification key can be derived just from the program without requiring any trust in the person who's deriving the verification key, right? It doesn't require any secrets for the trusted setup. It's like a transparent setup. Once you have you perform basically the ceremony once, and then you take the output of the ceremony, and then you can deterministically specialize it to produce this verification key. And anybody can check that this was produced correctly. And the benefit of this is that now when I'm a developer who wants to deploy the smart contract, all I need to do is I need to do this deterministic step of deriving the verification key, and then anybody can check that whatever I'm claiming the verification key is actually the correct verification key for the given program. Okay.
Now, one question I have is, could you have kept this as growth 16, but like the verifier inside here would verify Marlin circuits or something like that? Or is there an upside or downside to doing that?
Yeah, so you can do exactly that, right? So you can have, because really the only place where you need this universality is the program proof, right? Because that is, the programs are, there's like many programs with only one, this sort of transaction circuit. So you could put this as graph 16 and this as Marlin or Plonk or whatever is your favorite proof system. In the end, in Aleo, we just went with Marlin just for simplicity, so to avoid having two different proof systems in the code base.
In general, what are the other differences between like what you guys had in the original ZEXE paper versus what you guys are doing with Aleo now?
Yeah, there's actually quite a few differences. So I didn't explain it quite here, but in ZEXE, so we didn't actually just have one program for the entire transaction. What we had was each record was associated with both a birth predicate and a death predicate. So
and maybe explain those a bit more, because I think this is the first time those came up in this conversation.
Exactly right. So so let me just, maybe I can erase this because we're not going to be touching it anymore.
Yeah.
Okay. So what we said in ZEXE is that each record, there's two events associated with it. It is created in a transaction or is born in a transaction, and then subsequently it is consumed or dies in a subsequent transaction, right? So there's these two events associated with the record. So maybe we should allow the user to specify programs that happen at each of these two events, right? And in practice, what we found was actually we do need both of these events to even get simple applications such as private user-defined payments and so on, right? So coming back, so we have inside our record, so now these are no longer coins, these are records, right? So I'll change all of this later. So inside your record, you have this commitment, and inside this record commitment, we have our data, our public key, serial number, right? But we will also have a verification key that corresponds to the program or predicate that you want to execute upon the death or consumption of the record, and a program that is executed when the record is created or is born, right? So this is inside the commitment, okay? And the idea is that, so this actually results in a slightly different transaction circuit proof. So what we will do is we will, for each input record, check proof for VK against VKD, D, right? So because the input record is being consumed or is dying, we check that the user provides a correct proof against the verification key, the death predicate verification key for that record. So if there's multiple input records, so there's also like a R2, which is the input, then you also check the program proof against that VKD. And similarly, for each output record, right, check a proof against VKB. Right, so
and what kind of things would, so like the death predicate is more or less clear, but what kind of things can you enforce with the birth predicate? Like why do you need it?
Yeah, so it's actually a good question, right? So a priori, it's not clear why we, okay, so the record is born and it dies, right? So you have these two things, but you could also have 10 different verification keys or programs which are executed at various points in time, right? So, what can you actually put inside this VKD or VKB, right? So maybe by analogy, you can think of this VKD, for example, as being a private version of Bitcoin script, right? So in Bitcoin script, there's like the script you can associate with a particular UTXO, some script which is executed or is executed when the UTXO is spent, right? So this VKD is somewhat similar to that in that requires this predicate is executed or this program is executed when that record is being spent. Okay. In contrast, the VKB, you can, in some sense, I guess, think of it as a way to maybe propagate what we ended up doing in the ZEXE paper in terms of the application that we designed was the pattern that emerged was that this VKB was more like the application identity for that application, right? So if I'm doing a payment application, right, I would set this VKB to be the one which is doing the conservation of value. So it'll be the one that's saying the input value is equal to the output value. And the idea is that, so let's say if this C2 and C3 are supposed to be coins of token A, right? These records represent token A coins. Now I want to ensure that whenever a coin of token A is created, it is the case that the value is conserved, right? So what I will do is I will say a coin or a record corresponds to a coin of token A if it has birth predicate, which is the value conservation predicate for token A, right? So I'll specify some verification key, which is specialized maybe to token A, right? And that verification key will enforce that it'll look at all of the records in the transaction, check which all have VKB as the predicate, as the birth predicate, right? And it'll enforce that the value that is stored inside those records, the output value equals the input value, right? So you can think of this in terms of like the design pattern that emerged as we were writing the ZEXE paper. This becomes like the program ID or application ID for your application. This VKD becomes more like a spend condition. So it's like, this transaction or this coin can be spent in these conditions. So it can be like, okay, if there's a signature from not only the original sender, but also maybe some authority, it's more like something ad hoc that you can add on afterwards.
It basically seems like it's imposing restrictions on what the outputs could be or what the rules for creating outputs are. It's if the death predicate enforces a rule, who can, like, consuming the predicate, whether you can take it. This one says, well, the shape of the output needs to be
exactly,
something like that complies with whatever is specified by those predicates.
Yeah, exactly. So VKD sort of specifies the conditions under which you can under which this record is allowed to be spent. And VKB says that whenever a record of this type is created, it must satisfy these conditions at the time of creation. So this is kind of abstract, and I guess I'm not sure we have time to actually see how these interact in an actual application. But that's sort of the high-level takeaway.
But I think without this, like, you won't be able to do like sophisticated smart contracts and things like that. You would be very limited.
It becomes quite difficult. I think you really need both of those to actually get any non-trivial interactions. Is what we found in the paper.
That makes sense. Okay. All right, so that was one. Let's go back to the question of like what changed between ZEXE and Aleo, and like how things are different.
Yeah. So what we actually did in Aleo was we moved back to the previous model I had on the board, I guess, which was instead of having these input and output predicates, the death and birth predicates, we just had one program proof, which is responsible for the entire transaction, right? So then if this guy has some program VKP, then this guy also has that same program VKP, and this guy also has the same program VKP. So in some sense, we combine both the predicates into one at a high level, and we propagate all of those, the same predicate all the time. This sort of changes the design pattern that you get when you're actually designing different kinds of applications, but I think they're sort of, in the end, it ends up being equivalent. Though, so that's one change. So we go back to the simpler model. At least in the beginning, it's probably simpler for people coming from Ethereum land to reason about, for example, just one program in the transition or transaction instead of two different programs, right? Yep. That's one thing. And then the other thing was, we found in practice for many applications, function privacy ends up being compromised anyway the moment you have interactions with between multiple applications, for example, or with public state, or with, we going back to the earlier use case, some applications only need 1 in 3 out, some need 5 in 2 out. And in practice, you want to support those applications with the maximum efficiency. So it becomes a case of, it doesn't actually make too much sense to keep around function privacy because it gets compromised anyway, because you reveal these tiny clues which leak which application it is. So what we did was we sort of moved this program check outside so we don't have any zero knowledge proof recursion anymore. So we this is one proof, and then we include along in the transaction additionally the program proof, right? And this is the one which asserts that the proof is that the program executed correctly.
And do you guys have a distinction between like a private state versus public state, or is it all public or all private, or how does it work?
Yeah, so again, another thing was in ZEXE, we were trying to really go for, stretch the limit of, okay, what are the kinds of computations and what is a model for these computations that you can do when you want to have the maximum privacy, right? So this is why the strong focus on function and data privacy, right? But in practice, it ends up being the case that we also have the function privacy ends up being compromised anyways, right? And for many applications, you do need some interaction with some public state, right? So then you have to maybe leak some privacy from that aspect anyways. So ZEXE is was exploring one extreme of the spectrum, but in Aleo, if it was to support more normal applications, we do support like public state also. So you can reveal whatever's inside this commitment in the clear if it's needed, or if it's like some global state which must be interacted by multiple users at the same time, right? Then I guess I can explain what the problem with global state is quickly.
Yeah, I think I would be very interested in understanding, because I think public versus private state, as you said, like if there is like more than two people, or like 3, 4, I mean, maybe it's manageable, but as soon as the number is more than a few, you can't really do anything useful.
Yeah, exactly, right. So the problem at a high level is, okay, so let's say I'm interacting, for example, with Uniswap, right? Uniswap at a high level, there's like some balance for the various currencies that are stored in the contract, and some exchange rates that are associated with the result of the balances. All right, so the problem with global state is that, so again, with Uniswap, we were looking at the example of Uniswap. So the idea is that whenever a user transacts with the Uniswap sort of contract and updates their balances of, taking some token A and putting in token B, right? It changes the exchange rate for everybody subsequent who wants to interact with Uniswap subsequent to that, right? So this means that, but this is a problem in our application because, so what happens in Ethereum right now is that somebody just pushes the code to the network, and the miners execute that code, right? And then they update. So let's say there's 10 transactions wanting to interact with Uniswap in the same block. The miners will perform some serialization, some linearization of these transactions, and say, okay, this transaction comes first, then this transaction, then this transaction. And then they will execute this transaction sequentially, and then they will know that, this is how the state updates of the Uniswap contract as we flow through this sequence of transactions. Now, the problem with doing that in this UTXO-based approach is that I'm a user, right? I have run the proof, like I'm consuming, the state of the Uniswap contract is stored in some record, right? I'm running a proof which proves the correct execution of my exchange with Uniswap at the particular claimed exchange rate against the Uniswap record at time t, right? And then, this transaction is valid. But let's say there's another user who's trying to execute a Uniswap transaction at the same time in the same block, right? They will also try to consume this Uniswap record, right? But they won't be able to because the serial number for this one will already be in the list of serial numbers, right? So then basically you have to do one Uniswap transaction per block, which severely harms the throughput of these chains. And this is I think a problem that's being faced, for example, by Cardano right now. So one solution to this is to say, okay, we're not actually going to put the Uniswap transaction information or the contract information inside a record. It'll just be public state, right? And instead of having the user provide this zero knowledge proof of the correct execution, we will just let we will just do this on chain like we do with
like Ethereum and
like
others.
Ethereum,
yeah.
exactly, right? So the network will execute the Uniswap information against whatever the user provides, and then this basically now becomes a public computation instead of a private computation. Now there are some steps that you can take between this. You can, I think there's been some excellent blog posts that I've seen, which sort of propose a different idea where you you could have, for example, instead of having the network be the one responsible for managing the state and updating the contract, you could have some other party, like Uniswap runs some server, and the idea is that users send their incomplete transactions to the server sort of serializes and sequentially executes them, and then produces zero-knowledge proofs, and then only publishes those sequential zero-knowledge proofs, which are now valid because this record one is consumed here, and then the next transaction consumes the updated record, which is the output of this Uniswap transaction, so on and so forth.
Now, was this you still kind of like with a global state, with a public state, and you know what contract is being executed? You lose some privacy, but you still can retain some aspects of anonymity, right?
Yeah. So it depends on how you structure it for the particular application you have in mind. But yeah, so if you just reveal what data is being executed, then the commitments will still hide what public key and where the input data is coming from, for example.
Right.
So it depends on how you structure it. We're sort of still working through the full programming model in Aleo, what we want it to end up looking like. But yeah, there's not like you completely give up all privacy to get public state. There's probably like some spectrum of leakage that
Right.
you go through depending on how you design your application.
Like a Uniswap contract, as you said, it knows which records it consumes, but those records are not linked to anything that was existing before.
Exactly.
And then it maybe can enforce which records get generated, but again, somebody later consuming those records doesn't need to reveal which records they have used.
Exactly.
Okay. I think this concludes our session. Thank you so much, Pratyush.
Thank you so much
for the awesome session, and I hope everyone enjoys it.
Thanks a lot, everyone.
Thank you.
Bye.
Bye.